Earth is splitting apart right before our eyes. No, this isn't the plot of a disaster movie or some apocalyptic prophecy. It's real-world geology happening in slow motion across eastern Africa right now. The African continent is literally tearing itself in two, creating what will eventually become a new ocean basin millions of years from now. This geological divorce between tectonic plates is one of the most fascinating and dramatic examples of continental rifting on our planet. And today we're going to explore the science, implications, and future of Africa's Great Split. The East African Rift System stretches over 3,000 kilometers from the Afar region of Ethiopia down through eastern Africa to Mozambique. This vast crack in Earth's surface is the visible manifestation of a fundamental process in plate tectonics, the splitting of a continental plate. In this case, the African plate is divorcing into two separate plates, the Somali plate to the east and the Nubian plate to the west. It's essentially Earth's way of creating new tectonic real estate. What makes this geological phenomenon particularly fascinating is that we're witnessing continental breakup in its early stages. While most of Earth's major rifting events occurred millions of years ago, long before humans evolved, the East African Rift is active right now. It's like catching continental drift in the act, providing scientists with a rare opportunity to study how continents break apart and new oceans form. The mechanics behind this continental separation are driven by complex processes deep within the Earth. Beneath the rift, the mantle, the layer between Earth's crust and core, is behaving unusually. Hot, partially molten rock from the mantle is pushing upward toward the surface, creating what geologists call a mantle plume. This upwelling of hot material puts enormous stress on the overlying crust, stretching it thin like pizza dough being pulled apart. As the crust stretches, it fractures, creating the distinctive rift valleys that characterize eastern Africa's landscape. The most dramatic and active part of this rifting system is found in the Afar Triangle in Ethiopia, where three tectonic plates, the Arabian, Nubian, and Somali plates, meet. The Afar region has been called the closest thing to hell on Earth due to its extreme temperatures, volcanic activity, and otherworldly landscape. Here, the Earth's crust has thinned to just a few kilometers compared to the typical continental crust thickness of 30 to 40 kilometers. Magma chambers lie just below the surface, fueling active volcanoes like Erta Al, which contains one of the world's few persistent lava lakes. In 2005, the Afar region provided a dramatic demonstration of just how active this rifting process is. Over just a few weeks in September of that year, a series of earthquakes opened up a 60-kilometer-long crack in the desert floor. Incredibly, this rift, ranging from a few meters to 8 meters wide, formed in a matter of days, remarkably fast in geological terms. Scientists estimated that about 2.5 cubic kilometers of magma, enough to fill 1 million Olympic-sized swimming pools, had pushed up from below, forcing the land apart. This single event moved the two sides of the rift about 8 meters apart, which would typically take centuries under normal continental drift rates. What's particularly interesting about this event is that it showed geologists that continental breakup doesn't always happen gradually. Instead, it can occur in violent episodic bursts, with years or decades of relative quiet, punctuated by sudden dramatic events. It's like a geological version of punctuated equilibrium, where long periods of stability are interrupted by rapid changes. The rifting process isn't happening at a uniform rate across the entire East African rift system. In the Afar region, the plates are separating at rates of 6 to 7 millimeters per year, while further south, in parts of Kenya and Tanzania, the movement is slower, at around 1 to 2 millimeters annually. Even at these seemingly slow rates, over geological time, the cumulative effect is enormous. In a few million years, a mere blink in Earth's 4.5 billion year history, Eastern Africa will look fundamentally different than it does today. If the rifting continues as expected, the Horn of Africa, including Somalia and parts of Ethiopia, Kenya, and Tanzania, will eventually break away from the main African continent. The Rift Valley will widen and deepen until it drops below sea level, allowing the waters of the Red Sea and the Gulf of Aden to flood in, creating a new ocean basin. Madagascar, which already split from Africa millions of years ago, will be joined by a new island continental fragment. This future geography will dramatically reshape Africa, turning what is now a single coherent landmass into something resembling the fragmented island chains of Southeast Asia. The evidence for this future scenario isn't merely theoretical. We can already see the process in action at the northern end of the rift, where the Red Sea and Gulf of Aden represent more advanced stages of the same rifting process. These bodies of water began as continental rifts, similar to what we see in eastern Africa today, but they've progressed further, flooding with seawater and developing oceanic crust. The Red Sea, for instance, is only about 5 million years old, practically a newborn in geological terms. This progression from continental rift to nascent ocean basin follows a well-established pattern in plate tectonics. First comes rifting, where the continent thins and fractures. Then, if the process continues, the rift drops below sea level and becomes flooded, creating what geologists call a proto-ocean. As the plates continue to separate, magma wells up from below to fill the gap, solidifying into new oceanic crust. This is exactly what happened when the Atlantic Ocean began forming about 180 million years ago, as North America split from Europe and Africa. The East African Rift isn't just a geological curiosity, it has profound implications for the people who live along it. The Rift Valley has shaped human history in ways we're only beginning to understand. Fossil evidence suggests that many crucial steps in human evolution occurred in and around the Rift Valley, leading some paleoanthropologists to call it the cradle of humanity. The unique environments created by the varied topography of the rift may have provided the diverse habitats and selective pressures that drove human evolution. Today, the rifting process continues to shape life in eastern Africa in more immediate ways. The thinned crust along the rift creates pathways for heat from Earth's interior to reach the surface, resulting in numerous hot springs, geysers, and areas of geothermal activity. Countries like Kenya and Ethiopia have begun harnessing this geothermal energy for electricity generation. Kenya now derives nearly half of its electricity from geothermal sources, making it a leader in renewable energy in Africa. The volcanic activity associated with the rift also contributes to extraordinarily fertile soils in many areas. The rich volcanic soils support agriculture that feeds millions of people across eastern Africa. However, this fertility comes with risks. The same volcanic and seismic activity that enriches the soil also poses hazards to the growing populations living along the rift. One dramatic example occurred in 2018 near the Kenyan town of Mai Mahiu, when a massive crack suddenly appeared following heavy rains, cutting across a major highway and damaging several homes. While intensified by the rainfall, this fissure aligned with the underlying East African rift, highlighting how the long-term geological process can have sudden, unexpected surface expressions. The rift system also creates a series of lakes along its length, from Lake Turkana in the north to Lake Malawi in the south. These rift lakes have unusual properties. Many are extremely deep with unique water chemistry, creating isolated aquatic environments that have become evolutionary laboratories. Lake Tanganyika and Lake Malawi, for instance, host hundreds of species of cichlid fish found nowhere else on Earth, providing scientists with remarkable examples of adaptive radiation and speciation. The connection between the rift and climate is equally fascinating. The formation of the Rift Valley significantly altered regional weather patterns by creating a rain shadow effect. As the rift shoulders rose, they blocked moisture-laden air from the Indian Ocean, contributing to the aridification of East Africa over the past several million years. This climate change likely played a role in driving human evolution, forcing our ancestors to adapt to changing environments. Looking beyond the geological and environmental impacts, the rift also presents both challenges and opportunities for economic development in the region. The potential for geothermal energy is enormous. The rift countries could theoretically generate far more electricity than they currently consume. This clean, renewable energy source could power economic growth while avoiding the carbon emissions associated with fossil fuels. Mineral resources are another potential benefit. The unique geological processes along the rift have concentrated valuable minerals, including gold, platinum, nickel, copper, and rare earth elements. Tanzania's Williamson Diamond Mine, one of the world's oldest continuously operating diamond mines, lies within the western branch of the rift system. Ethiopia's Danakil Depression, part of the Afar Triangle, contains vast salt deposits along with potash minerals essential for fertilizer production. However, extracting these resources presents challenges. The same geological instability that creates mineral deposits also complicates infrastructure development. Roads, pipelines, and buildings constructed across active fault zones risk damage from earthquakes and ground movement. Additionally, many of the most resource-rich areas are remote and lack existing transportation networks. Water management represents another complex issue. While the rift lakes provide freshwater resources, they're vulnerable to climate change and human activities. Lake Turkana, for instance, has experienced dropping water levels due to upstream dam construction in Ethiopia, creating potential for cross-border tensions. As climate change intensifies, competition for water resources may increase, potentially exacerbating regional conflicts. The science of monitoring the rift's development has advanced dramatically in recent decades. Satellite radar interferometry now allows scientists to detect ground movements of just a few millimeters across vast areas. GPS networks provide precise measurements of how tectonic plates are moving relative to each other. Seismic arrays record the multitude of small earthquakes that accompany the rifting process, helping geologists map the subsurface structure in 3 dimensions. These technologies are creating unprecedented opportunities to observe continental breakup in real time. During the 2005 Afar rifting episode, for example, satellite data allowed scientists to detect the intrusion of magma beneath the surface even before visible cracks appeared on the ground. This kind of monitoring capability helps researchers understand how continents break apart and may eventually improve hazard prediction. Despite these technological advances, questions remain about how exactly the East African rift will develop. Will the entire rift evolve into an ocean basin, or might the rifting process stall in some sections? The historical record suggests that not all continental rifts successfully progressed to ocean formation. North America's Rio Grande Rift and the Rhine Graben in Europe are examples of failed rifts that began the continental breakup process but stopped before reaching the oceanic stage. The timeline for Africa's eventual split also remains uncertain. At current spreading rates, it would take at least 5 to 10 million years for a narrow seaway to form, and tens of millions of years for a significant ocean basin to develop. However, geological processes rarely proceed at constant rates. As we saw with the 2005 Afar event, episodes of rapid change can accelerate the timeline in unpredictable ways. What seems certain is that the face of Africa will change dramatically over geological time. The continent that future generations inhabit will look fundamentally different from the one we know today. New coastlines will emerge, new islands will form, and the distribution of natural resources, climate zones, and habitats will shift in ways that will reshape human settlement patterns and economic activities. For geologists, the East African Rift represents a rare scientific opportunity, a natural laboratory where continental breakup can be observed and studied in real time. For the people living along the rift, it represents both challenges to navigate and opportunities to harness. And for all of us, it serves as a powerful reminder that our planet remains dynamic and ever-changing. The seemingly solid ground beneath our feet is, in geological terms, as fluid and changeable as the oceans themselves. The African continent's slow-motion split offers us a humbling perspective on the timescales of Earth processes. While human civilization has existed for mere thousands of years, the geological processes shaping our planet operate over millions. We're witnessing just a brief moment in Africa's geological evolution, a snapshot of continental divorce proceedings that began long before humans existed and will continue long after our time has passed. The Great Split reminds us that even the most fundamental features of our world map, the shapes of continents and oceans that we take for granted, are temporary arrangements in Earth's long history of constant change.